resource estimation. This is a fairly major chapter within the best practices, and it deals primarily with the factors in estimating a mineral resource and the documentation that's required to follow up and report the estimation process. There are a number of major subheadings within the mineral resource estimation best practices that the CIM deal with, and they highlight the following areas in particular and detail what their expectations are for each of those. Firstly, they look into and discuss the data density, the integration of geological information in the resource estimate, the listing and recording of the data sets, the data analysis, statistical and geostatistical, which takes part of the process, the sample support and ensuring that all samples should be equal in their support as part of the estimation procedure, the economic parameters which are taken into account, the mineral resource model, how it's put together and how it's evaluated, the estimation techniques which are employed as part of the interpolation and extrapolation, and how the mineral resource model is validated. So within this major topic of mineral resource estimation, we're going to look at each of those subtopics in more detail over the next coming few slides to provide us with an indication of what's expected in terms of best practices from the CIM. So let's have a quick overview initially of the mineral resource estimation process. As we can see, it's a fairly complicated procedure and involves many steps from the beginning of the process, where we're gaining and assessing the initial information, the informing data where drilling is undertaken, sampling, logging, and then assaying, which are done externally, and then that information which has been placed into the database, and the quality assurance, quality control processes which are required, which we've described earlier. We then come into the geological interpretation process, and we've just outlined the best practices as set out by the CIM in respect to geological interpretation. We then go on to the area which we're going to look at in more detail now, which involves the coding and compositing of data, the types of statistical analysis and domaining which are then required, top-cutting strategies which may be employed, and the variography, which looks at the variability of grades and assays over distance and how that's used in the estimation process, how parameters can be optimized and tweaked to ensure that we get the best estimate for the data that we have, and how that can be built into a block model which can be used therefore to evaluate the deposit in terms of the economics and mine planning, the search neighbourhoods which are defined, which is the size of the area which is used to take samples and how far they're used to interpolate grades, how the estimation may be performed, the types of density values that we have, in terms of that being an important component for evaluating tonnage, how the end model is validated, and finally the classification and reporting procedure which is then involved. That primarily is the data analysis and resource estimation component which we're going to have a look at within these sub fields over the next few slides. Beyond that, once all of that process is completed and a report is filed, the project will involve a written report, which normally would involve some type of technical report or internal report to detail the estimation process in more detail. A sign-off is required from the QP to state that they're happy with the process and that it conforms to industry best practices. An external audit may be conducted, an outside person, or sometimes an internal audit where those parameters and that process will be checked to make sure it's reliable and working properly. The resource then is handed over for reserve evaluation, and as a component of the validation we'll also reconcile those numbers, particularly in terms of the reserve, against production to make sure that the reserve estimate that we're reporting to the public is in accordance with the types of tonnages and grades that we're seeing and producing from underground as the ultimate check. So let's now move on to the first of the subjects within the mineral resource estimation component: data density. So it's important for the QP first of all to assess whether there is sufficient data for a resource estimate to be able to be conducted. If the data is too far apart, or if the data is of a poor quality, if it's not representative of the mineralization, if it's been drilled in the wrong fashion, if it's been drilled down the dip of a vein system, or if it doesn't truly represent the type and style of mineralization which we understand to be present, then there could be fundamental problems and errors in the estimation process. So it is up to the QP to decide at an early stage whether there is sufficient data to allow an estimate, and whether that data is drilled close enough together to allow a reasonable representation of the style of mineralization, and also to comment whether that data is suitable in terms of its quality to allow an estimate to be conducted. For example, as we can see in this cross section, we have a densely drilled set of information, and that's allowing us to be able to provide a reasonable understanding of the geological and mineralized structures, and therefore we would be quite confident in terms of stating that we have enough information to be running an estimate. The next component within this resource estimation process is the integration of geological information. Data must be integrated into and reconciled with the geological interpretation according to best practices. Consideration must be given to the limits and geometry of the mineralization controls, and internal waste areas. So it's very important for us to use all the geological information available, particularly with such items such as mapping from underground, to be able to define our three-dimensional mineralized structures and to check to see whether they're following the style of mineralization as we're encountering it underground, and the geometry is properly orientated, and the limits of the mineralization and internal waste structures that we're seeing are replicated in the model that's being generated. Again, with all mineral resource estimation processes and with any models and any type of evaluation conducted, geology is fundamentally the key. If we do not follow the geology carefully, if we do not reconcile it and check that we are establishing a good geological model and following that model, then we will always have issues and problems with the estimate and forever being trying to correct and reconcile against poor results and numbers. As part of the resource estimation, we also require listing and recording of the data sets. So all data and information used in the mineral resource estimation must be identified, catalogued and sorted for future reference. So upon completion of the estimation process, or even more preferably during the process, all the information which is being generated should be catalogued and stored in a safe and secure environment, either on a main server or on an external drive, and should be backed up in a way that if an external auditor wants to check the methodology and the linear process, they can refer back to that full data set. Sampling, sample preparation, assaying practice and methodologies must be clearly described and the reason for the choice explained. So we must ensure that any preparation, grinding, crushing and assaying of particular samples is done in an appropriate manner to give us the most representative grade assays for the type of mineralization which we're attempting to model. And particular care should be taken in recording, analysing and storing data and results from QA/QC programs. So once again, there is a very strong emphasis on quality assurance, quality control, making sure that a program is set up and it's being continually followed. So within Fortuna we have a series of procedural manuals and protocols which allows us to dictate exactly what type of analytical techniques are to be used and what type of grade ranges, and our expectations in terms of how samples will be taken, both in terms of channel samples and drill hole samples, and the type of quality assurance, quality control programs, insertion of blanks, standards and duplicates to ensure that we're monitoring the precision and accuracy levels of the assays and samples that we're retrieving. In that way we have a repeatable mechanism to try to ensure that we're getting the best types of results on a continual basis and we're not introducing artificial biases into our evaluation that may give us a poor result in our estimates. So let's have a look at the next sub-chapter, the data analysis. There are a number of components that the best practices recommend in terms of conducting data analysis. The purpose of the data analysis is to improve the quality of the estimation by understanding the statistical and spatial character of variables. This includes the establishment of interrelationships between variables, the relationship, say, between two coexisting elements which we may be interested in, gold and silver or lead and zinc. The recognition of spatial variation of variables, so how much variability we're likely to see over distance between two samples. If we have samples which are very close, they're more likely to be similar, and as we increase that distance, the similarity between samples is going to get less and less, and we have a particular methodology of monitoring that variability, and that must be recorded and used in the evaluation process. Domaining is of utter paramount importance in the estimation process. Again, this boils down to geology and ensuring that we have continuity within particular domains where we have a similar style of mineralization, and identifying and understanding of outliers. So in some circumstances we may get extreme values which are much higher than our standard distribution of grades, and these extreme values, although possibly correct and real in terms of what's been encountered underground, they can create a huge problem in the estimation process by smearing high values across long distances which are unrealistic when it comes to mining. So we must be able to identify these extreme values and then deal with them in an appropriate manner to give us the best estimate possible. Also, understanding of the nugget effect is important. The nugget effect is the level of variability at zero distance. It's the inherent variance that we see essentially at the analytical level. So if we take a crushed, powdered form of the pulp and we run an analysis, and then we take that same powder and reanalyze it, there will be a level of variability that we see dependent on the material and the type and style of mineralization, the sizes of the grains of the element of interest. So, for example, gold can often be very, very highly variable at very short distances, really between two separate analytical evaluations. And that's why it's called the nugget effect, because it's similar to having the effect of a gold nugget, which creates variability over extremely short distances. And there are a number of plots and evaluation tools and techniques that the QP and estimator uses in running his checks and determining specific outliers and issues with nuggets and the relationships between different elements. If we continue further the data analysis in terms of the best practices, it talks about two particular areas where it expects certain evaluations to be conducted. In terms of univariate, for a single element, the analysis should include statistical summaries of key indicators such as mean, standard deviations, minimum, maximum values, coefficient of variations. So these should be reported as a standard component of evaluating a particular element. Also, should be a part of the evaluation is to generate histograms to see the type of grade variability that exists within a particular domain, and also probability plots, where we're going to look at the type of variance that occurs and check to see if we have any extreme outlier grades. Additionally, there are some bivariate analysis which are recommended as part of the best practices. When we have more than one element and we're looking at two or greater, we should be looking at the correlation between those elements to see if there is a strong positive or negative correlation between those two elements of interest. For example, if we're looking at gold and silver, do we see a similar increase in the silver grades when the gold grades increase, or do we see that the silver grades decrease when we get an increase in gold grades? This is important because we want to make sure that we reproduce that correlation when it comes to the estimate. Another way of checking the relationship between these two elements is by plotting them as a scatter plot, and plotting the grades of the gold and comparing that to the same plot grades of the silver grades at the same XYZ points. And also regression analysis may be important in checking to see what type of evaluation there is between those two elements or greater. In terms of multivariate analysis, when we're dealing with 3 and more elements in the same deposit, we may look to do multiple regression analysis. For example, if we have are interested in densities, we may be able to evaluate what the density is based on numerous metal values and be able to work out that using a regression. And we also may be able to create variable plots, multivariate plots, such as triangle diagrams, to see how different elements react and are related to each other, and therefore we can ensure that these types of evaluations and effects are represented within the block model. Continuing the data analysis theme, We're also interested in the variographic analysis, which is the correlation that exists for grades over distance in 3 dimensions. So the grade variability will increase as we generally increase over distance. We also are interested in the outlier recognition and treatment, and we must be clear and stating how we are going to identify extreme values and the methods that we're going to use to adjust the estimates to deal with those extreme values, whether that's top cutting or using a restricted analysis. In the example here on the right we can see a variogram, and we see here that on the left axis represents the level of variability between 2 sample points, and on the x-axis we can see the distance between those 2 sample points. So at low distances towards the y-axis we see that the variability is less, there is more of a correlation between the samples, and if we were to plot that on a scatter plot we would perhaps see something a little bit like this. Then, as the distance increases, the variability increases and we get more of a scatter until we arrive at what we refer to as the range, or the sill in terms of the y-axis, and that is the maximum level of variability that we expect to see within the particular domain. That would be essentially just a scatter plot with there being the lowest amount of correlation between samples that is essentially the background noise, and anything greater than this distance as indicated by the range is of no longer any use to us in terms of the estimate, because it's essentially just random variability beyond here, and there is no longer any correlation between one sample and another. So we're going to now move on to the next topic within our estimation. We're going to look at the sample support, and this refers to the size, the shape and orientation of samples, and it requires conformity to improve the estimate. You might remember that we may be taking different length samples if it's drill holes, or perhaps the drill core is of a different diameter dependent on how easy it is for the drilling, and therefore the volume changes. And the important thing with the samples is that if we have a dramatic difference in the volume that's being analysed, it can have a dramatic effect on the estimate, as larger samples would have a greater influence as compared to smaller samples, but this wouldn't be represented in terms of the estimate, because the estimate only sees this as point data. So it would treat these samples in exactly the same manner, and that would be unfair on the evaluation, because maybe some very small samples are taken because the geologist sees some higher grades in those particular areas, and therefore those lengths have to be standardized to give them exactly the same weighting. So this is represented in terms of the selection of the composite length, and this has to be appropriate for the data and the deposit. So we need a dominant assay interval length, and we need to think about the vein thickness. So for example, if we have a deposit which we're drilling as shown by the red line, maybe the samples have been taken similarly to how the red lines are being shown here, with some having quite long sample lengths and others may be of more interest having shorter sample lengths. And we also can look at the grade contour here, and we can see that we are in a waste zone, then perhaps a low grade area, and then a high grade zone before returning to a waste zone with fairly sharp boundaries. In this particular situation, the modeler has chosen to composite based on the full length of the geological vein thickness. So in these initial components, the composite is within waist, and then we move from the hanging wall to the foot wall for a full composite length in the low grade, and then again the same hanging wall to foot wall in the high grade. As long as we have a similar type of composite length, we're seeing similar types of lengths within the same domain, then we can say that we have a similar sample support and feel confident that these then will be treated equally and that we will get a representative estimation. Okay, so we're going to now move on to the next subchapter, and that involves the economic parameters. So the economic parameters which are generally involved with the resource estimate are normally orientated around the cutoff. And again, we come across this statement within the CIM best practices that the cutoff grade must use a reasonable prospects for economic extraction. So the cutoff grade can't be set too low, as that would represent an over-optimistic viewpoint, and a lot of that material would not have reasonable prospects for economic extraction. So we have to have some idea of what the end product is in terms of how the deposit is going to be mined, a rough idea of the economics which are involved, and we can have a look at potentially other styles of mineralization and mining scenarios if we're not presently operating in that environment. If a mine is set up and running, then we have a good idea of what type of cutoff grade we are going to be encountering when we come to production. So the cutoff grade must realistically reflect the location, deposit scale, continuity, assumed mining method, metallurgical processes, costs, and reasonable long-term metal prices. So all of those components are taken into account when the QP decides on that cutoff grade. Variations within the resource model that may require more than one cutoff grade in different parts of the deposit must be an ongoing consideration. So if we're mining a more remote part of the deposit, or if we're mining at much deeper levels, then it may well be a consideration to set a different cutoff in accordance with the costs which are going to be involved with mining in those different, more difficult, more inaccessible areas. And therefore we may be looking at applying different cutoffs dependent on the material or the location. So let's have a look at the next chapter in terms of the best practices, where we deal with the resource model and estimation technique. The model parameters that are going to be used for the estimate should be developed based on mining methodology, deposit geometry, and the grade distribution. So that really is partly based around the types of block sizes which we're going to be using in creating the model to make sure that they're representative of what we're going to be encountering and attempting to mine further down the field. The choice of the estimation technique should be based on the geology and complexity of grade distribution within the deposit and the degree to which high-grade outliers are present. So there's a whole series of different possible estimation techniques which the resource estimator may use and has at his disposal, and he has to make an informed decision based on his geological knowledge and his experience with working in a particular style of mineralization over a minimum of 5 years. He must decide what he feels is the best technique based on what he's encountering and what style of mineralization he's expecting to encounter underground. The estimation method must be adequately documented, so a description of the methodology needs to be included within a external technical report or in an internal report. It must be clearly detailed how the estimate has been conducted. And estimates may include everything from a nearest neighbour polygonal estimate through more complicated mathematical methods such as inverse distance weighting and ordinary kriging, all the way up to extreme computing mathematical evaluation techniques such as conditional simulation and the generation of recoverable resources. As long as the QP can feel justified at explaining the reasoning behind the usage of a particular technique, then they should feel comfortable with being able to stand up in front of their peers and explaining the reasoning behind using that. The best practices outlines a number of different techniques that it expects is in terms of the validation of the resource model once it's completed. Firstly, the resource model must be consistent with the primary data. That's of uttermost importance. Obviously, everything that's constructed and generated in terms of the final resource model is based on the primary input data. Therefore, the two have to be closely integrated and related to each other. So, the CIM best practices lists a number of particular validation steps that should be included. These are a visual inspection of the estimated grades in plan and section compared to the input composited data. There should be a check for global bias to make sure that the estimate is providing a similar set of numbers as the global set of numbers for the primary data. There should also be a check for local bias to make sure that there's not over smoothing and that the local grades around high composited data are similar and lower grades are found around the localized areas where low grade composites have been encountered. We'd also want to check for a change of support if it's required, dependent on the density of data and the variability of data. We do want to ensure that we don't over smooth the estimate. And it's also important to reconcile the resource model and the reserve model in particular back to the production data which we see. This is the ultimate check, and if we're seeing in terms of production similar to what we're seeing in terms of the resource model, reserve model predicting, then that's an extremely good sign that the evaluation is working. It is also necessary to re-evaluate if the economic parameters to confirm their suitability. So we want to maybe check those economic parameters, make sure that they're current and up to date and applicable with what we're seeing presently, and also check perhaps some sensitivities. The mineral resource must be classified as either measured, indicated or inferred, and no other type of classification. The method used for classifying must also be clearly documented within the technical report or an internal document. So we must detail how we've come to the consideration to classify within each of those categories and why we've chosen that particular classification. So let's have a quick exercise to see in terms of model validation what your opinion would be in terms of these block models in terms and respect to the raw input data used. We have an image here on the left and we see the block model coloured with the same coloration as the dots of the channel input data. So what is your opinion of that model to the left? Do you believe that it's validated and that the model is representative of the input data? And how about the model to the right? Certainly, as a QP, I think it would be very concerning if you were to, as part of your validation, see the blocks on the block model to the left. It would indicate that something has gone wrong in the estimation process, and you'd have to return and begin the estimate again to try and uncover where the problem was. Certainly the block model on the right seems to be doing a lot better job in representing the input data that we see. Let's have a look at another example. Again, we see the channel samples in terms of the strings and the block grades in terms of the block model. What's your opinion in terms of the evaluation here? Is the block model validated okay, or is there a problem? In my opinion, it looks like that the block model is representing reasonably the block grades that we're seeing within the channel information, and that would be a good indicator that the estimate is performing reasonably well. An additional tool to that is running a Swath Plot, where we take slices through both the block model in terms of a particular type of estimation technique such as ordinary Kriging, and we compare that to a polygonal type estimate or nearest neighbour estimate, and we see how the two match up and see whether they are comparable in ensuring that high grades are estimated where we have high grade samples and low grades are estimated where we have low grade samples. And in that sense we can then check to see whether the local grade variability is reasonable. Another technique which we can have a look at is in terms of the mineral resource estimate compared to what we're seeing in terms of production from underground as part of the reconciliation process. So we have an example here where we have the estimated model shown in the green to the left, and we see the amount of tons mined, and we see the grades of that material. And in the blue is what we're actually seeing in terms of production related numbers, the mineral in situ, and again we have the tons and the grade, and this has been estimated based on the channel samples that we've been receiving as the production has been occurring through that area of the estimate. On the far right here we see the difference between the two sets of information, and for example here we can see that we have a good estimate in terms of the second semester of 2013, where we have very little variation between what has been estimated in the block model, with a difference of only 3% in the tons and 3% in the gold and 1% in the lead. Anything which is going to be below 10% is going to provide us with very good confidence in terms of the numbers. We can see a much higher number and therefore more concern where we're seeing the numbers in terms of the difference for the second semester 2014, where we're getting a 26% difference in terms of the tons and a 13% difference in terms of the grade. And here we can see that there may be a particular reason when we run an additional investigation where we found that the mineral in situ The material that we've been able to mine has found that their veins are much thicker than what was originally modelled. So you can see here the vein interpreted using the longer term model and the veins using the short term model, and the difference between the two here, which means that we're getting a lot more tons in this particular area, and therefore that can explain to us where we have a particular problem or issue in our geological model, and in the future then that can be corrected to ensure that we get a better correlation between our production and our estimation. The reconciliation is an ongoing process, and it's something we're going to return to towards the end of this presentation to provide a little bit more detail into the expectations of what's required in terms of best practices.